video, we're going to discuss confidence intervals for population means when sigma is unknown. Right? And then we'll do an example. So first we're just going to discuss the idea of these confidence intervals, and then we'll do an example where we use those formulas that we're about to discuss. All right, so first let's just remind ourselves what's going on here with confidence intervals for population mean. So somewhere from negative infinity to infinity, there lies a true population mean that's unknown to us. So we go out and we get a sample, and we estimate x bar, right, from that sample, the sample mean. And so that's one point estimate, right? So I want to create a confidence interval where I go above and below x bar, certain margin of error, and I create some sort of interval to say it's a 95% confidence interval. Then I can make a nice statement such as I'm 95% confident that mu lies within this interval that I've just provided, right? So in general, the confidence interval for population mean will be x bar minus some margin of error, and then x bar plus some margin of error. Okay, so how we calculate this margin of error, though, that's really what we're going to be talking about right now. Okay, so in the past, we've talked about this formula. E equals z alpha divided by 2 sigma over square root of n. So this is the when sigma is known situation. All right, so we've talked about this before. So now we're changing up the situation, and we're going to say when sigma is unknown, right? So when sigma is unknown, you can't use this formula because you don't know sigma, right? So you're going to have to use a different formula. We'll use formula coming from the t distribution. So instead of the z distribution, we're going to be using t critical values. And then instead of having sigma here, we'll have s, which is the sample standard deviation, and it'll be over the square root of n. Okay? Now, let's talk about the criteria in order to be able to use this. So in order to be able to use this formula, the data must be normally distributed. Must be normally distributed. All right, so data must be normally distributed. They must say something about the data being normally distributed. Otherwise, you cannot use this equation. All right, now that restriction is not so tough with over here. In this world, when we had sigma is known, the data could be normally distributed. Data has two options. It can be normally distributed, can be normal, or it could be not normally distributed. Can not be normally distributed. Now, if it was not normal, the sample size would have to be large, greater than 30. Okay? If it was normal, it doesn't matter if the sample size is large or small. But if the sample size is small, so if n is less than 30, sigma must be known from some sort of outside resource. Sigma must be known. The population standard deviation must be known. Right? If n was greater than 30, in either scenario, if n is very large, then you could approximate sigma using the sample standard deviation. Okay? So S would then approximately be equal to sigma. All right? So when n is greater than 30, you can always kind of use this equation whenever n is greater than 30, whenever the sample size is greater than 30, because central limit theorem kicks in, and then you also have this nice result that the sample standard deviation is close enough to the population standard deviation that you can just go ahead and use that as an approximation as long as n is greater than 30. So this over here is really only for when n is less than 30, and then you must have this requirement that the data is normally distributed. If the data is not normally distributed and the sample size is less than 30, neither of these work for you. Okay, that's outside the scope of this course, so we won't be discussing that in this course. So that's when the sample size is small and the data is not normally distributed. Neither of these margin of errors will work. All right, let's go on. Let's talk about an example. A researcher is interested in knowing the average weight of newborns within Washington state. A random sample of 20 newborns are weighed. Their average weight is 3,500 grams and a standard deviation, or with a standard deviation of 538 grams. Okay. This is the sample standard deviation because they're talking about the sample in this sentence, right? They're saying that this is a random sample of 20 newborns, this is their sample average, and this is their sample standard deviation. So let's go ahead and write down this information actually as I'm reading it. N equals 20, X bar, the sample average, is 3,500 grams, and S, the sample standard deviation, is 538. Assume that newborns' weights are normally distributed. Great, we needed that, especially with the small sample size. We're going to have to use the equation of E that involves this T, S, over square root of N, right? Because of this small sample size, right? And because we were not given the population standard deviation, rather we were given the sample standard deviation. So we're going to have to use this equation. We're going to have to use this equation for the margin of error that involves the T distribution. All right, so calculate the 95% confidence interval for the mean weight of all newborns in Washington state. All right, so I'm trying to calculate X bar minus E with mu in the center, X bar plus E. All right, so I need to determine what E is. So first thing I should try to figure out is what is this T alpha divided by 2? What is this critical value? I got to go to my T table. Now when I'm going to my T table, I'm doing a 95% confidence interval. So the area in the middle is 0.95. So the area in the tails is 0.05, right? I mean, you divide it by 2 for each tail, but the total area in both the tails is 0.05. So when I'm going to my table, I'll look up 0.05. Also, when I go to my table, what's the degrees of freedom? So degrees of freedom is for the T distribution, and it's always n minus 1, right? So in this situation, it'll be 20 minus 1, which is 19. Okay, so I'm going to look up 19, and the area in the tails is 0.05. Let's pull up our table. All right, 19, here we go. Degrees of freedom is 19. Area in two tails is 0.05. There we go. Here it is, 2.093. 2.093. All right. Okay, let's use it. So 2.093. There we go. There's our critical value. So let's start plugging things in. E equals 2.093. S is 538. N is 20, so the square root of 20. Okay, let's pull out our calculator and calculate this. 2.093 times 538 divided by square root of 20. Okay, go ahead and press enter. So 251.7888. We'll go ahead and round to 3 decimal places so that 8 will become a 9. So 251.789. 251.789. All right, so there we go. There's our margin of error. So now we just need to plug that in over here, and we'll have our confidence interval. I'm going to go ahead and move the screen over. So I have the X bar, sample mean, which was 3,500. Minus the margin of error, 251.789. Mu is in the center, and then 3,500 plus the margin of error, 251.789. Okay, so pull out our calculator one more time for this. So we'll do 3,500 minus 251.789. All right, I'll go ahead and round to 1 decimal place now. So 3248.2. 3248.2. Okay, put mu in the center. Then over here, I'll have 37 51.8. Right? So we can be 95% confident that the mean birth weight of newborns in Washington State is between 3248.2 grams and 3751.8 grams.